Hello, welcome to another lesson of sectoral structures theory. Today's lesson is building on the prior lesson that we talked about, which discussed reducible and irreducible sectoral structures. And a quick reminder, we said that a sectoral structure is irreducible if we take all of its parts and the greatest common divisor for all of them is 1. And the structure, that makes it irreducible. And the structure is reducible if the greatest common divisor for all its parts is greater than 1. And what it's really saying is if we have similar looking or almost identical looking sectoral structures where the only difference are the number of sectors, then the simplest form of these sectoral structures is what we call the irreducible form. We also introduced the dal function right here, which gives us the which reduces any sectoral structure to its simplest irreducible form. Now we will talk about isomorphic sectoral structures. This is not the same use as in group isomorphisms. This is a little bit different. We will borrow a lot of terms for sectoral structures theory. So when we are saying isomorphic, we are really saying that they look exactly the same. What the only difference is the number of sectors. So let's really define it. If we have two sectoral structures, AN and BM, then we say the two structures are isomorphic if they have the same irreducible form. In other words, if we do dal of AN and dal of BM and we get the same result, then we say that the two sectoral structures are isomorphic. Let's look at this example here. We've got AN is 4, 2 squared subscript 8. Dal of AN is 2, 1 squared 4. We have BM, which is 6, 3 squared subscript 12. Dal of BM is 2, 1 squared 4. So we got the same result for both. Therefore, we say the sectoral structure AN and the sectoral structure BM are isomorphic sectoral structures. We will also use the same symbol for congruent or isomorphic. Now, notice that all theta structures are isomorphic to one another, and we said a theta structure is simply a circle divided into equal sectors, and they can all be, because they can all be reduced to 1 subscript 1. On the other hand, if we have different xi structures, which are of the form 1 raised to the power of n subscript n, then no two unique xi structures are isomorphic. If we have two xi structures and we know that they are isomorphic, then they must be the same sectoral structures. They must be identical. So we want to differentiate between identical and isomorphic. And that's why we're using these different terms. Additionally, if we have two sectoral structures and we know that they are both irreducible, then the only way that these two are isomorphic is if they are identical as well. So these two examples, they must be the same structure. In other words, no two irreducible structures are isomorphic to one another. No two unique structures are isomorphic to one another. And this is really important because if we start thinking of structures in terms of their irreducible form, then we realize that each of them is unique. Of course, this is an equivalence relationship. So if AN is isomorphic to BM and BM is isomorphic to CP, then AN is isomorphic to CP. Let's look at two more or three more applications. Let's assume we have two sectoral structures AN and BM, and we are gonna join them continuously, so via an alpha joint. Keep in mind here, when we're joining them, this is different than some other branches of mathematics where we are just gluing. That's going to be something else. In this case, we are joining and then we're shrinking the overall structure so that the length of the curve remains 2 pi. Because if it's not 2 pi, then this is not a sectoral structure. It's just a sectoral sequence. Going back, so AN continuous with BM gives us CP, and we're using the wedge symbol. And let's assume that dal of CP is equal to dq. Then we can say that AN continuous with BM is isomorphic to dq. Let's look at another similar application. AN, this time we're gonna say alternating with BM, so we're gonna join it via a beta joint. So AN alternating with BM gives us ES. Dal of ES gives us, this should be equal, gives us FT. Then we can say that AN alternating with BM is isomorphic to FT. And I really, this is really going to help us in our next lesson. We want to differentiate between equality in this setting and isomorphic to in this setting. They are not identical. Let's look at another concept. Let AN be an irreducible sectoral structure. So irreducible, such that the order of AN is greater than 1. If you remember, I said the order 1 sectoral structures are always the odd ones out. So if we look at AN, which is both irreducible and has an order greater than 1, and then we're gonna do the following operation. We will say AN alternating with BM. And all we know is that AN is irreducible and has an order of 2 or greater. Then the resulting sectoral structure is also irreducible. So this is the first rule we can discover from this concept. So let's say we have the sectoral structure, for example, 2, 1 subscript 3. This is an irreducible sectoral structure. We're going to alternate this with the sectoral structure 4, 2, 2 subscript 8. So this is irreducible, this is reducible. So let's alternate them, see what we get. We get 2, 1, 4, 2, 2, and then subscript 11. Now I want to say two things about this. First of all, this resulting structure is clearly irreducible, and you can check that, meaning the greatest common divisor of all of these is 1. And all we needed was one of these to be irreducible, so that the result will be irreducible. If both of them are irreducible, it will also be irreducible. I want you to notice that this is the reverse form, so we can write it as 2, 2, 4, 1, 2, 11. So this is really the reverse of it, and in this setting, we're gonna say that this is a free, or the concept of isomorphism is a free operation, not a bound operation, if you want to review that lesson. meaning that it doesn't matter whether we're looking at the reverse or whether we're looking at the standard format. So whether we look at this from here to here or from here to here, it doesn't matter when we're talking about isomorphism. Let me say this another way. So if AN and BM in standard form are isomorphic to one another, then the reverses of both of these will also be isomorphic to one another. Therefore, this is a free, not a bound operation. Thank you.